Hello everybody, this is Static Electricity, and for the first 5 learning objectives, we're just looking at electric charges and electric field. The next part, we're going to be looking at electrostatic charging by induction. So nothing too earth-shattering, things that you actually know about, so let's just dive into it. So the first part is stating that there are positive and negative charges, and charges are measured in coulombs. Whoa, what's that? So if you take a look at this over here, we know, right, that if you look at an atom, inside an atom, there's going to be 3 main things. You have the did I say positons? The protons, the protons, the neutrons, and electrons. Uh, I'm pretty sure you know which is which, right? Okay, so you probably may not be able to figure out which is a proton and neutron in this picture, but electrons, the ones that are on outside, correct? Now, what's most important to know over here is that what charges are going to be associated with the protons and the electrons. So just like everything that we can measure, when we talk about charges, we need to talk about it in terms of the measurement. So I measure things which are far in length, in meters, correct? So how do I measure charges? Charges are going to be measured in something called coulombs. So what is 1 coulomb? Well, to put simply, you have positive charge, you have negative charge. So let's say I have one charge, which is 1 coulomb, which I'll put as 1 in capital C. Well, that's a positive charge. I could also have a negative charge, which is negative 1 coulomb. Well, that's how it basically looks. What's more important over here is this statement over here, where you state that unlike charges attract and like charges repel. This is going to sound very similar to how magnets work, and yeah, that's basically it. So what happens if you have positive and positive? Well, these are like charges. In those cases, you're going to have something, an interaction where it repels. Negative and positive, of course, this is going to be one which is they attract. Likewise, this one. And finally, negative and negative, they would repel. I don't think you needed this table. I think it's pretty straightforward also. But the question comes down to actually why do they actually repel? Isn't it? Why is it attraction and repulsion? This is where you need to understand something known as the electric field. So how do we define electric field? The description is it's a region in which an electric charge experiences a force. Now, this field definition is very similar to how we talk about gravitational field as well as magnetic field. So let's look at that whole manner in which it's being defined. So if you think about it this way, that there's always this template in which how you would define fields. If I talked about a gravitational field, right? A gravitational field, so if the word here is gravitational field, it's a region in which an object or a mass experiences a force, right? What about magnetic field? Magnetic field is a region in which a magnetic item or magnetic object experiences a force. So in this case, using that same template of what a field is, an electric field is a region in which what experiences a force? Is it any object? If in a magnetic field, I talked about it in terms of a magnetic object or something which is a magnetic material. In this case, we are talking about a region in which an electric charge experiences a force. So what are those forces? Is it a repulsion or attraction? So how do you explain those things? So now let's look into what an electric field actually looks like beyond just describing and defining. So in this diagram over here, we actually see 2 charges, and we'll get to that soon. Let's look at just one charge, and we shall begin with a positive charge first, and let's see what is that electric field that comes from a positive charge. So I want you to imagine that we have this giant metal ball or metal sphere, and I'm going to put this metal sphere on this object over here. Let's call this an insulated stand such that no charges can move on this, right? We know charges can only move in conductors, right? So electric conductors. So this is an insulator. Now, in this sphere, which is very, very positively charged, I'm going to put these pluses over here just to show it's really, really positively charged. Now, what would you assume would happen if I have this tiny little smaller sphere, and the sphere over here, let me draw it a bit better. Let me draw it a bit more. Let's draw it a little bit bigger. Okay, now, and in this sphere, this is positive charge too. Now, if I were to bring this object close to this more positively charged sphere, what direction would you expect this to move. Let's assume this is very heavy, stuck here, and this is free moving. Let's say there's a little string that's being attached to it, right? Where will it go? Would it still hang in this position, or would it move away? Now, you would know from what we have understood from the previous part, which is in terms of interactions, if I have two positively charged objects, right, the interaction with repulsion, and the repulsion in this case would be a direction of force that way, away from it, isn't it? And if I were to put this same sphere over here, it will push in this direction. Likewise, if I put it over here, we know that it'll push it away, correct? Now, what happens if I were to look at this? And let's call this over here a charge that I'm going to use to test that interaction. A charge which I'm going to use to test with the direction of forces as I move it around. I'm going to call this, therefore, my test charge. And is it positive or negative? Oh, hey, it's a positive test charge. I spelled that wrongly, positive. So using this positive test charge, I can kind of map out what is all the interaction, all the forces around a positive charge. And I can now say this. I could summarize it to say that for a positive charge, I know that the electric field would be something like this. And you say, hold up, that doesn't make sense. I have all these things, all these lines. What do the lines mean? Well, what I mean is that if I were to draw the direction here, like this, with the arrowheads pointing out, it tells me that if I were to put a test charge near it, this is the direction in which the force would be experienced, right? So let's look back again. An electric field shows the region in which an electric charge experiences a force. So if I put it here, what is the force I experience? It will go that direction. Now, likewise, if I change this to a sphere which is negatively charged, what do you expect the electric field to look like? Instead of repulsion, it will be attraction, right? So everything will seem to go inward instead of outward, and therefore, I'll get something that looks like this. So you imagine that all the things will be going inwards because this is when I'm testing with a positive test charge. Remember this one here? If I were to put a positive charge somewhere here, I know the direction of force would be this way. Now, are the lines significant if I do more lines, less lines? What's the significance of all the lines? Well, it's easy to put it this way. Which one do you think is the strongest and weakest charge? A, B, or C? Now, just by looking at it intuitively, you see, whoa, there's so many more lines here, right? So many more electric field lines. So this is definitely going to be the one that's strongest. And yes, right, the field lines actually show how strong the electric field is. Not just the field lines having many, but also the distance between the field lines will tell you how strong it is. So let's zoom in over here just a little bit, okay? Now, if I were to have an area, okay, just a region. Now, let's compare a region here. Okay, let me just circle out this region here and a region here, okay, as similar size. Now, where do you think would be stronger? Where will I feel that electric field? Oh, no, so let me put it that way. Where would I have where will I have the greater electric force? In this region down here or region out here? Now, in this region, you see that it contains many more electric field lines compared to that region over here, correct? Yeah, so yeah, when they're closer together, the lines are closer together, that's where they're stronger. When they're further apart, they're weaker. And this becomes very important when we look at charges interacting with one another. And that's where you have things like these. So let me try to animate this if I can. Let's try to turn it around. There we go. So you can see one of them is positive, one is negative. Of course, what's not very good about this diagram is that you can't tell which is positive, negative. But something's interesting about the diagram is it seems like, and if I just look this way, the field lines seem to be closer in the middle. There we go. Something like that, right? They seem to be very close over here. And the further away we go, the lines seem to spread out a bit further out, isn't it? Now, we're not going to be drawing it in 3D for our exam papers. We're going to draw it in 2D. But you must see that when I'm closer to, when the lines are closer, it means it's stronger. And the further away I go from my electric charges, of course, the electric field is going to get weaker. And the distance between each line is going to get further and further apart. So how do we draw it in terms of our syllabus? We will remember these two things. One, the closer the lines, the stronger the field. And two, the arrows of the lines must indicate the direction of the force. So let's place one positive charge here and a negative charge over here. Now, how will they interact? We know that electric field shows where it will go. So if I were to play a test charge here, it will be repulsion from the positive and attraction towards the negative. For that reason, I know there should be a straight line going between both of them, and that direction should be this way, correct? Now, if I were to put the electric charge here, it will push out this way, correct? But around here, it would be attracted to the negative charge, going this way, isn't it? So there will be something that looks like this on both sides. Now, take note that as I draw it, I will try to be as symmetrical as possible from the top to the bottom, right? Now, here's the thing. I'm not going to get the same strength, electric field strength, here compared to here, correct? Because the further I go, the weaker electric field would be, which means that I need to draw a even bigger field line this way. Oh, they are not very symmetrical, but okay, you get the idea lah. And now the other side, something like that. Still need to draw the arrows. So you can tell the further it goes away from here, the electric field is not going to be as strong. Remember, how close the lines are shows me how strong it is, and well, the distances are getting further apart, not as strong. Oh no, what do I draw over here? Now, here's a question. Should I draw it like this, outward, or should I draw it like this, inward? Right, so I want you to imagine, it's not just anyhow drawing, spreading out the things here and there, but remember these are going to be lines that go bigger and bigger and bigger. So this over here doesn't make sense, correct? It's still going to go one big round. So when you look into your textbook and you see the lines going this way, it's not that it's ending, okay, it's not this one, it's not that it just goes nowhere, but I'm imagining that my box is this big, and this is actually going bigger outside and connecting it this way, okay? What I draw on the other sides, so this one I can assume to go in here and here. Let's try. Over here, what is the direction of arrow I should put? Remember, I use a positive test charge placed here. Where should it go? Positive test charge with my positive charge, I will get a repulsion. So it goes this way, right? Does it mean that over here, it should also go outwards? No. Put a positive test charge here. Does it get attracted or repelled? You remember that it gets attracted, so it goes this way, right? Oh no, is there something wrong with these two over here? Yes, something is wrong with it. It is not going out, it is actually going in, going in. So these two are very, very usual errors that students make, and I'll own up lah, I actually made a mistake, sorry. This way should be going inwards, right? Sounds good? So always out of the positive, into the negative. Out of the positive, into the negative. All right, one more drawing and we're done. What happens if they are similar in charges? What if I'm going to have two positive charges this way? What would a drawing look like now? They're both positive. Well, let's think about it. If I have a positive test charge here, it wants to repel. If I have positive test charge here, it also wants to repel, but it's also being pushed by this away, correct? So I'm going to have something that looks like this. Repel, repel, downwards also repel, and repel. Now, how do I draw this part over here? Does it turn inward like the previous one, or does it turn outward? As you can tell, if this one goes inward because it's connecting that giant electric field, this is going outward, right? So it goes like this. Out, out, everything is going outward, right? So over here, you can still draw that straight line. It's going to go away because it repels. Here also is going to go away because it repels, right? In the middle over here, you're going to have no electric field, right? Because they're pushing against each other. It will be a bit different if this has a charge of 1 coulomb and that over there has a charge of 2 coulombs. Now, if that were the case, the electric fields would look a bit different when all of these parts would be stronger than all of this over here, so you have a very skewed image. But we'll have more of those discussions in class. All right, so what we have here so far is that we have understood that when we have positive and negative charges, we measure them in coulombs. We know how they interact, where unlike charges attract, like charges repel. Psst, by the way, this one is usually always tested. This is usually the first thing you must mention in an explain question, which we'll do next time. We also know how to describe electric field in terms of this over here, region in which an electric charge experiences a force. We know how to draw an electric field. Ooh, this is being blocked. Oops, oops, oops. Yes, there you go. We know how to draw an electric field for just an isolated point charge. That means just one charge. We know the directions, and we are able to draw an electric field between two isolated point charges. So not just positive, negative, we also can do positive, positive. Question, what if they are both negative? What do I do? It's actually the same diagram as this, except that the arrows would now be going inwards because we use a positive test charge to see where the field line is going. Makes sense, right? If there's negative, negative, all the arrows would then just go inwards. All right? Oh, please don't get confused by this. This is just an example, okay? This is not what's happening here and here. All right, 17 minutes. Not too bad. All right, take care. Bye.